Partial fractions, math review. You learned partial fractions in your math class, probably for calculus doing integration. This is a review of what you already know, also to introduce you to a new technique for doing partial fractions that's very fast. Partial fractions is the case where you have a ratio of polynomials and you want to rewrite them as a sum of ratios of polynomials. You factor the denominator, and then the trick is to figure out what the constants in the numerator are. Let's take this example. X minus 2 over x squared plus 3x plus 2. We want to write it as a over x plus 1 and b over x plus 2. We start by factoring the denominator on the left-hand side and writing it out explicitly. We then find a common denominator for all the terms. Distribute the algebra in the numerator. Rearrange the algebra to put all the x terms together and all the constant terms together. From here, we know that the constants for the x's have to be equal to the constant for the x on the left side, and the constant terms on the right side have to equal the constant terms on the left side. From that, we get two equations and two unknowns, which can be solved through a number of methods. We wind up with a is negative 3, b is 4. Therefore, x minus 2 over x squared plus 3x plus 2 is negative 3 over x plus 1 plus 4 over x plus 2. What if you have repeated roots? I changed the problem a little bit. Now the denominator is a perfect square of x plus 2. Here we need to write it as that perfect square term, but we also have the term without the squared. The algebra is very similar to what we saw before, where we have the squared term and we have the two terms that are being added together. We factor on the left-hand side. We get common denominators on the right-hand side. Distribute our terms in our numerator. Rewrite things such that our x terms are separated from our constant terms. And again, our x term coefficients have to match our x term coefficients on the left, and our constant coefficients on the right need to match our constant coefficients on the left. Therefore, we wind up with this set of equations, two unknowns, again solve, and we wind up with x minus 2 over x squared plus 4x plus 4 is now equal to 1 over x plus 2 plus a negative 4 over quantity x plus 2 squared. Now I want to introduce you to a new method called residuals. I call it cover one up because that's how I think about the process for doing it. We're trying to solve the same problem. The problem has not changed, partial fractions. Our technique's a little bit different. We still start with factoring the denominator on the left-hand side. Now, instead of trying to get a common denominator, if we're trying to solve for the a, we're going to multiply through on both left side and right side by the denominator of a. On the left side, the terms cancel out. On the right side, the terms cancel out. And now, if we set x to negative 1, which was the denominator of our original a term, our b term is going to go away. And remember that x is negative 1. We now know that a is equal to negative 1 minus 2 over negative 1 plus 2, or negative 3. That's how it works. That's really why it works. We can do the same thing to find our b value. Factor our denominator on the left. Multiply through by the denominator for the thing we're trying to find. The terms are going to cancel, so we have a variable we're trying to find. That term cancels and goes away on the left-hand side. Now we set our variable to the value that makes that original denominator term for our x go to 0, which will make our a term go away. And that x value is negative 2. We plug it in. b is now negative 2 minus 2 over negative 2 plus 1, or 4, positive 4. This is a summary, because I just showed you why it works. But we don't need to write out all those steps just to do it. How can we just do the things which really need to be done? What's really being done in this process? The factoring we still need to do. But now if we're going to try and find our a term, we'd look and say, okay, this is our denominator. x plus 1. What value of x will make that term go to 0? A value of x is negative 1. We take that x plus 1, cover it up, or at least figuratively, we can cover it by just ignoring it, plug in our negative 1 values, and that's our a value. Likewise, to find our b value, remember that our a variable had a value of negative 3. Cover up that term that was our denominator for the variable we're trying to find. Plug in the value of the variable that makes that original denominator go to 0. So x plus 2 is 0 and x is negative 2. And that's the value for b. What about if we have repeated roots for the residual method? A lot of it's the same as with the algebraic method, and a lot of it's the same as with the residuals with non-repeated roots. We still need to have the example of the squared term and the non-squared term. I'm going to make it more complicated than the other repeated roots example to show you how to do it with residuals. We take our function back to our denominator, and if we're trying to find the a value, we're going to look at that x plus 1 term, make it go away, plug in negative 1s for all of our x's, and that'll be our a value, same as before. But now, instead of going directly to this b term, we're going to go to the highest denominator of the repeated roots. Starting over again, cover up our repeated roots, plug in the value of x that makes that denominator go to 0, and that's our value for c. Now at this point, we're pretty close, but we still need to find a value for b. There is a method with residuals for doing this. It involves taking the derivative of a quotient, which I find not to be pleasant. Instead, I prefer from here to go to the algebraic method. Same as what we were doing before, but because we now know 2 of our values, it's a lot simpler. We do not need to solve 3 equations, 3 unknowns. We need to solve 1 equation, 1 unknown. That's a lot more tractable. So let's look at where we're at. Same original problem, but we know our a value and we know our c value. Get a common denominator. So we need to multiply the a value by x plus 2 quantity squared, our b by x plus 1 by x plus 2, and our c by just x plus 1. Notice that's not squared because we already have squared in the denominator. At this point, let's look at the numerator. We know the denominators are equal. We're good there. Back to where we were with the algebraic method. We have no quadratic term, we have a linear term, and we have a constant term. And over here we've got a mixture of quadratic terms, linear terms, and constant terms for all the different coefficients. The quadratics on the left should match the quadratics on the right. The linear on the left should equal the linear on the right, and the constants on the left should equal the constants on the right. If we had 3 equations, 3 unknowns, we'd have to solve all 3 of those equations. But we don't have 3 unknowns, we only have 1 unknown. So we can pick any one of those equations to solve that we like to. And usually the x squared term or the constant term are going to be the quickest because we can do them by sight. In this one here, we've got an x squared times negative 3. Doesn't matter what the rest of it is. Here we've got an x squared times b. And here we have no x squareds times 4. And we have no x squareds over here. That's quite often the case with the x squareds. There's a lot of zeros because they don't always appear. So we wind up with 0x squareds on the left, negative 3x squareds plus bx squareds on the right, and 0x squareds again for that last term. So b has to be a positive 3 for this to work out. 0 equals negative 3 plus b equals 3. Alternatively, we could have looked at the constant values. We have the negative 2 on the left. If we were to square this out, we know we're going to have a 4 for the squared here, so we'll have 3 by 4, negative 3 by 4. We know here our constant term is going to be 1 times 2, which is just 2, so b times 2. And here our constant term is just 1, 4 times 1. A little bit more algebra to work on, but b will be 3. We'll also wind up with b being 3 for the linear term, but that has a lot of different things. We got to figure it out. We have the 4x here. We have the FOIL. We've got the 1x by the 2x. the 4x, so there's a lot of different things going on, so the linear terms can be a lot more complicated. We don't need it. We just saw that we get it with the quadratic term and we get it with the constant term. Use either one of those. Both of them return a b value of 3. You're going to use this partial fractions to solve other things for this chapter. Hopefully you can use this in other courses as well. The residual method I find very easy and quick to do, usually faster than typing it into a calculator. There's a handout on this. Look for that also on this website.